All right, we'll give folks a few minutes to join. Mateo, your background gives me so much to look at. I love it.
Yeah, thankfully my room is in a bit of less of a mess of this, but still.
It's awesome. All right. Well, it is 3, so sorry, Eastern time. It's time. And so why don't we start and other people will join as they can. So first, let's like to introduce Mateo Merli. He's our StreamNative CTO, and he will be leading you through our monthly updates this time. Thank you, Mateo. Can't hear you.
Okay, now should be better.
Yes.
Hi, everyone. I will start with some of the updates, and then we will do a deep dive on one of the feature and one of the newest, not newest, but like newish features of Pulsar. So on the update side, we do have the Pulsar Summit Europe coming up. So it will be held on October 6th, and you can register there. And the CFP just closed, but the sessions and keynote will be announced very soon. So let's keep an eye around. We'll be announcing the lineup very soon. On the releases front, there have been quite a few releases in this month. So the first one is the 2.7.3 release. We keep like the previous minor version. We make sure that we want to be patched with the latest fixes that we get on the 2.8 branch and master, so that is very stable and just fixes are backported, and so security fixes or like software bugs. And the 2.8.1 as well would be the first patch release for 2.8. Again, it is in the process, so probably towards the end of this week should be ready, or like at the very late the start of next week should be 2.8.1 should be out. Again, there's not a lot of fixes since the 2.8 was a very big release. So we'll pack in a bunch of fixes there. And on the client libraries, the Go one, we have a new release, 0.6. Again, bug fixes there, but there is also one interesting new feature, which is the support for open tracing. So if you want to have integration with open tracing, that's a good one to have in the Go client. And Node.js also, there is a new release. This is the officially supported C++ version of the Node.js client. And the new feature there, apart from bug fixes, is the support for end-to-end encryption. So the end-to-end encryption was already supported in Java, C++, and so on. So this has been added to the Node.js client as well. On a side note, there is also some people working on a pure JavaScript library, so that will work with Node.js without needing C++. So that would be an interesting one to follow on to see how it develops. I think at this point it is very alpha code, but it would be interesting to have at some point a pure JavaScript library that comes without the burden of installing like RPM packages, or where you need that JavaScript application. And that's pretty much very short summary of what happened the last month. There is also like many proposals that are being discussed. I will try to cover them in the next 3 iterations. There are new interesting features and improvement proposal that would be very nice when they get finalized. But this month I wanted to talk about one of the newish feature, as I said. So KeyShared was the last subscription mode that was added in Pulsar, and it was added like around maybe a year and a half ago. And it has went through some maturing period, and at this point it's becoming like quite stable, and it's a very powerful tool to have, and allows the application to simplify a lot of the logic. So if you look at what KeyShared is, first let's do a quick recap of subscription types. So when we say that the subscription type is kind of independent on how the data is published, so you can have multiple producers sending data into a topic, and then you can choose how to consume that data, and that the choice is based on the application need and on the use case and so on. And you can also mix and match different types on the same topic. So the basic one is exclusive, so only one consumer is allowed to attach the subscription. That's very easy. If you have a second consumer, you get error when it subscribes. And the second one is failover. Failover means that there is only one active consumer on the subscription, and the other one will be in standby. Now, failover is interesting also in the context of partition topics. So if you have a partition topic, essentially this active standby is replicated across the partition. So the idea here is that we want to spread the active consumers on all the partitions. So if you attach a consumer to a partition topic and is the only one, it will be the active on all the partitions. If you start another consumer, then it will be, say, 5 and 5 each. So it's kind of like a round-robin assignment of partitions to consumers. And that's very similar to the way the Kafka consumer group work. I mean, not very similar, it's somewhat similar, I would say. The assignment is similar, but in the personal case, it's much more lightweight, the assignment. There is no zookeeper or there is no ownership. It is all done by the broker here. And these are the ones that are where the old school and ordered kind of type of subscription. And then there are like more dynamic ones. So the shared is basically you can attach any consumer to this subscription and the delivery will be done out of order. So there is no ordering guarantee there. Messages can be spread across all the consumers. If a consumer crashes, the messages that were sent to this consumer will be resent to another consumer. So the end is very flexible. So you can add and remove consumers depending on what kind of traffic you have. And but again, if you don't need ordering. So the question is, we have like one very dynamic type shared, and then we have more static type like failover. So if you use failover and if you want to increase your consumers, so if you have 10 partitions and you want to use 20 consumers, you need to add more partitions. It is the only way, right? It's the only way that you have in Kafka as well. So instead, you want to have a more middle ground scenario here. So the KeyShared is exactly that. So the KeyShared essentially it lets you connect multiple consumers to a single subscription, and it will give you the ordering guarantee per key. So you will not get all the messages for that are sent on that partition, but you will get them all the time the same keys and in the same order. So that's important because basically you get the pros of using failover, so you get order delivery, but you also have you can also like dynamically scale the number of consumers irrespective of the number of partitions. So let's talk a bit more about that. So it's essentially a more granular and flexible way to do message routing. And the guarantee here is per key. Typically like if you look at in failover, you have basically per partition ordering. But at the end of the day, you route messages to partitions, and the property that you are interested with is not just to consume the data in the partition is a key. So that's why we don't need to have per partition ordering, but you need to have some kind of like application domain property, which is represented by the key, to have your ordering guarantee. And the other property is the stickiness of a key to one consumer. So the same key will be sent to the same consumer in order. And finally, that we can basically scale up consumption without changing number of partitions. So you can even have one single partition and you can have 100 consumers on that subscription, or you can have, say, 10 partitions and 100 consumers. But partitions essentially are orthogonal to the number of consumers at this point. The only reason that you want to have partitions is if your traffic is very big and that one single broker cannot sustain the traffic of that topic. At that point, you want to use partition to spread across multiple brokers, but that's a different discussion from the number of consumers. That number of consumers typically depends on how expensive it is to process the messages. So you might have some messages, some events that are like very expensive to process, and you need to have many consumers, but you might not need many partitions, and that's when KeyShare is a very good model here. So again, the way it works is that the topic is still a log, right? So the data is stored in order in the topic, and in this example, like we have key 1 value 0, key 2 value 1, key 3 value 2, and then it repeats. So the idea here is that each consumer will get a subset of these keys. And we use hashing on the key to make sure that whenever we want to dispatch a message to any of the consumers, we take the hash of the key and we decide which consumer is selected for that hash range, so that will ensure that the same key will go to the same consumer. Now, when we do add consumer, then we have to do some careful handling to make sure that there is no overlapping period between when a key is supposed to go to one consumer and then it starts to and then can go to a different consumer. One other thing that I wanted to also point out here is that the ordering here is guaranteed at the delivery. So that means that you will be guaranteed that your consumer will get all messages in order, and there will also be that when we switch, you will also be guaranteed that the new consumer, if you add one more consumer, the same key that was on consumer 1 will not be seen on consumer 2 until everything was acknowledged by consumer 1. So it is also like a more strict than what failover provides. There is no like window for race condition here. So everything has to be acknowledged by the other consumer before we can start delivering the next part of keys to a new consumer. So there's one question here. So what happens if a consumer dies? Does automatic routing to the remaining consumer? So if a consumer dies, basically these hash ranges will get reassigned, and I will get a bit more in detail down on later on. Essentially, like the key ranges gets reassigned to the existing consumer. So if, for example, like say if consumer 3 crashes, now the hash ranges in which key 2 was falling, now they're unassigned. So they will get to be reassigned between consumer D1 and consumer D2. At that point, these messages will get replayed to either consumer 1 or consumer 2. If you look at the API, so enabling the KeyShared, the basics, the default setting is just simple as changing the subscription type. This is the same as you could say exclusive or shared or failover. So inside it, you just have to specify KeyShared, and everything will get working from there. When we are scaling up, as I mentioned, some of the keys will have to be shifted, right? So if you have 2 consumers and now you add the third one, now you want that third one to have the same share of traffic as your other 2. The idea is that we want to make sure that the hash ranges are equal across all the consumers, so that the resulting traffic should be similar on all the consumers, because otherwise you might get a consumer that is the bottleneck, while the other will receive less traffic. And there are a few mechanisms that we have to assign the ranges to a consumer. The default is a method that is called like an auto split, but there are different ways in which we can assign. So the default one is splitting and merging of adjacent hash ranges, and the second one is a consistent hashing mechanism. So if you look at splitting and merging, essentially, like you have you represent your hash space as a ring, and you divide that ring into equal segments. So in this case, let's say that you have if you have a 16 bits, like up to 65K, your hash is an integer here, and you just basically assign across C0, C1, C2 an equal set of numbers. And the idea here is that when a consumer joins, we take the biggest of the ranges and it gets split, so that the new consumer will take over some portion that was before to another consumer. And when it leaves, that's it. For example, if C1 in this example leaves or crashes, what happens is that this hash range 3 will get split in two and merged with C3 and C2. So they will both get half of that key space. So this mechanism has a few pros and cons. Jumping back and forth. So the main pros here is that the data structure is very compact to handle this, and you just have to have basically a tree map with 5 elements here, one per consumer, and you can figure out what is the range that this ORAC, which better question is here is that which is the consumer that is handling this hash range, so that if I have this message, this key, I take the hash, I get a number, and with this number I can figure out which consumer is owning that message, is supposed to receive that message. Now the cons of this approach is that depending on how consumers are joining and leaving the group, the distribution can be more or less skewed. In the simple case, it will get good distribution, but if you're like bad luck that consumer live in a wrong order, it can be easy to get tricked and to have some consumers that have like a 2 or 3 or 4 times the hash ranges of all the consumers, and therefore getting different amount of traffic. One other approach that we have added, I think it was added in 2.7 actually, is consistent hashing. The idea is that this should be also becoming the default in 2.9, hopefully. There is a setting in broker.conf, so you can just say subscription key share using consistent hashing equal true in broker.conf, and the broker will use this different method. So with consistent hashing is a normal approach for this kind of problem, right? But the idea here, the objective is that we want to minimize the reassignment. So we want to have that each consumer, so 2 goals. First, that each consumer will have the same number of keys assigned to him. And the second one is that we want to minimize the number of reassignments. So whenever a consumer joins or leaves, the keys that are shifted should be the least possible. So the main idea about consistent hashing is that you still have these hash ranges, but instead of having 1 per consumer, in this case you have n, and with default n is 100. That means that you have your key range, and you throw 100 points in that ring when a consumer joins, and you remove all these 100. But there is no merging, so the merging and splitting of these ranges is natural. So you just put basically you add this consumer 100 times into this tree map essentially. And one other property here is that we have chosen to is that these points are based on the hash of the consumer name. So consumer joins will be taking the hash of itself and then mix it with the index and throw like 100 points in that ring. And each consumer will do the same. And then eventually, like when you want to look up the consumer for one particular message, you take the key, you take the hash, you go and check whichever is a consumer, one of the 100 points of that consumer that is close to that point, to that hash. The pros of consistent hashing is that the spreading comes very naturally. So by having by using like hashing and like 100 times hashing, and the spreading is very natural and normal, so that it is like if you have only, if n equal 2, you get a poor distribution, but with n equal 100, you get a very good distribution already. And the other thing is that you get to minimize the reassignment of keys. So with n equal 100, essentially the number of keys that are getting reassigned when a consumer joins or leaves is actually 100th. So it's 1 over n, the keys that are getting reassigned to new consumers when there is like a join or leave event. And finally, another pro is that it is possible to have a predictable and repeatable assignment. I mentioned that we use the consumer name. So we take the consumer name and plus the index from 0 to 99 in this case to have all the 100 points. That means that you can have a consumer that comes back up and will receive the same keys because we have the same point. So you can leave and join back again and receive the same keys that you were receiving before. Because again, that is all predictable, irrespective of what happens in between, right? In the final state, if you pass the same consumer name, you will end up receiving the same keys. One of the cons, though, is that to achieve this good distribution, we use n equal 100, which is a good default. But if you end up a lot of consumers, like I say, thousands and thousands of consumers, this might use more memory compared to the other approach. So now you have different options. You can either use the split and merge, or if you have lots of them, or you can reduce the n number. So if you have thousands of consumers, you can use, say, n equal 10 or n equal 5 even, because anyway, you have a lot of consumers already. So that is already having a good distribution. But again, so the idea is that consistent hashing is a better default because it's easier to reason about. Finally, there is one other option here, which is the static assignments. In some of the cases, so the dynamicity of assignment is good in general, but in some cases, application might not need that. And actually, they want to have a more fixed set of consumers. So let's say that if you want that when a consumer crashes, you don't want to replace it with an existing consumer. Instead, you might want to wait for that consumer to come back up. This might be the case, for example, like let's say that you have you have some kind of like recovery policy in the consumer deployment levels. For example, your consumers are running in pods, and you know that pod will get, if that pod crashes and the consumer fails, you, instead of like reassigning the keys to other consumers, you want to have you expect this pod to come back up at some point later. It can be very soon or like in a few minutes. We don't know, but you have some mechanism in place so that if one pod is down, the scheduler will bring up the pod somewhere else, and you will have your existing set of consumers. In this, or like for example, like if you're doing like a running upgrade of these pods, you might not want to have these keys going back and forth. Instead, you want to keep the keys on the same consumer. And for example, like one reason about that could be that this pod might have some durable state. For example, like if you're, since you're doing like order consumption, you might have, say, receive messages with the same key and store that into a shard of the database, and that shard is stored locally by that consumer. In that case, you will not want that if the consumer is down, these keys will go to somewhere else, because that shard, it is owned by that consumer. So you cannot do this dynamic reassignment. Instead, you might want to specify that I'm receiving, I want to receive a portion. Say if I have 10 consumers, I could just like precise that I want to receive the first 10% of the hash range. If I'm consumer 2, I will receive the second 10%, and so on. So each consumer will get the same hash range that will compose 10% of the entire key space. At that point, if that consumer goes down, these keys, messages with these keys will not get delivered until a consumer will come up and say, oh, I want to have received that, that key range. So you lose the dynamicity, but you get a very predictable and very simple behavior here. And that is good if you do have durable state typically on the consumers. That is, and you have some mechanisms to restart these consumers as well. So that is typically when you want to do that. And okay, so the way that you declare that is that you have you can specify a policy when you do the KeyShared subscription. And in this case, the policy is a KeyShared policy sticky compared to the auto split, which was the one before. And on this sticky policy, you can configure a list of ranges. So here I'm just passing one, but basically it can be an array or a list of ranges. And a range is essentially like two numbers, like is like the first hash and the last hash here. And this is based on like a 16-bit hash space. That by default that hash space can also be increased, but in this case, I'm specifying that I want to receive only the first half of the hash range, and that is on the assumption that some of the consumer will ask for the second half. Now we'll talk about more of the gotchas. So there are a few things that are like very specific to KeyShared, and things that work that you need to be aware of when using KeyShared. That might not be a concern with other subscription type, but they are concerned with the with KeyShared. The first one is the choice of the routing key. That is very important, and the second is the how batching interact with the KeyShared, and finally the impact of slow or faulty consumers that can have on the overall consumption. So the choice of key, of the ordering key of the message is very important because the key is what determines a good distribution of messages across the consumers. And if you don't have a good distribution, what happens is that you will have a skewed assignment to consumers. So one consumer will get more messages than others, and that consumer might become the bottleneck. And you could add more consumers, but if you don't have a good cardinality of the keys, that won't help, because since we have to guarantee that ordering and stickiness, all these keys that might be skewed will go to a few consumers. So if you do want to have good distribution, typically, like since this is hashing and is based on statistical assignment, the rule of thumb here is that you might want to have an order of magnitudes more keys, unique keys than number of consumers. So if you have 10 consumers, you cannot have, say, 15 keys unique. That will not have a good distribution across the 10 consumers. But if you do have 100 keys that with over 10 consumers, that will pan out quite well. So that's kind of like very general rule of thumb. And then within that, it's important also to consider the distribution of events per those keys. So you might have many keys, but you might have, say, some of the keys that will have a lot more messages than other. That's typical. But if you have like a huge spike of traffic into one single key, and then that might result in a spike of delivery or backlog to one consumer that we get clogged with a lot of more events than other consumers. So again, this is something that's typical. Like if you see any uneven distribution of traffic across consumers, that's something to think about. How many unique keys I have, and how well distributed are the events per those keys. And final note is that sometimes people will publish messages with no keys and try to consume with KeyShared. In that case, again, to maintain the guarantee, no key is one special type of key, so that we all get to one consumer. So just be careful of that. So if you see that only one consumer is getting the data and the other ones are not, there's good chance that these messages will not have been assigned one key. So just double check that. The second part is batching. So the key part here to keep in mind is that in Pulsar, like, we treat batching as a purely client business, and there are many reasons for that, but mostly is efficiency. So a batch is packed and compressed by producers. So a producer will, if you configure batching, which by default it is configured, it will assemble a batch, and of all messages, it will compress at the end. Eventually, it can also be optionally encrypting that batch with private key, and then it will send to the brokers. The brokers will not look into the batch. The brokers and bookies, basically, they treat the batch as a black box. We just look at the metadata before the batch to understand how many messages are in this batch, what is the person name, and so on. But we are not looking inside at the batch because that would be very, very expensive to break that batch in the broker or the bookies. We just want to have access to one single RPC to publish, and then get stored in the bookies, and then it's one single response back. In a similar way, the consumer will receive the batch. So the broker will dispatch one batch or multiple batches, and the consumer will receive the batch, decrypt, decompress, and then it will break it down into individual messages. So the problem here is that that KeyShared goes a bit against the best practice that we have on other subscription type, in that by default we try to batch as much as possible because if you build big batches, that will head to less batches, which means less interaction between clients and brokers and bookies, and so it becomes more CPU efficient. And it will having bigger batches will lead to better compression. So if you enable compression, if you have a batch of 1 or 3 messages, we compress a lot of less than a batch of thousands items. So one of the key and best practice to efficiency is to make sure that you have a good batching factor. But this goes a bit against KeyShared, because since the broker can only route a batch to consumers, we cannot have this batch to contain multiple keys, multiple different keys. And the reason for that is that if you have key A, B, and C, we can take a hash on key A, but that consumer will get messages that are not belonging to him. So it's a bit of an issue here, but there are two solutions to this. So one is to disable batching. That works. It will increase the CPU, as we say, because there is more work to do between client and brokers and bookies because of this, and less compression. The other option is that you can use the key-aware batching, and this key-aware batching will only pass messages with the same key into a given batch. Now, here your mileage might vary wildly, in the sense that depending on how many keys and your traffic distribution, it might help you a lot, or it might help very little. It might actually, in some, like if you have a lot of keys with like per key throughput very low, it might just be better to just disable batching, because that, so the key aware batching will not be able to do much improvement over that. So you might just better off that disable batching. But on the other side, like if you have say a fixed set of say 100 keys, or like a small number of keys, and each key has a lot of events, that the key aware batching will help you a lot. So again, just make sure you understand whether it makes sense or not. There are cases in which it makes sense, cases in which it makes not sense. And the final effect here is, this is more like a side effect of the guarantees that we offer. So we say that we do offer the strict ordering of messages. So we want to make sure that if a consumer will receive messages, it will not receive an earlier message because of some combination of failures. And one example to consider is that you might have consumers joining and leaving in different orders, in different fashions, and so for example, like it can become very complicated here. So you might have consumer C1 that gets assigned keys 1 and 2, and now you have consumer C2 joins and then it gets some of the keys. The catch here is that we cannot send immediately the messages for key 2 to C2, but instead we have to wait until everything gets acknowledged. Because otherwise, if C2 will receive messages and then it fails, we have to send it back to the C1. At that point, you might get the out of order there. So that's what we want to avoid. So to avoid that, instead, consumers typically are joining the subscription into a post state. That means that if you're joining this, subscribing this topic, and there are existing consumers already doing the KeyShared thing, and the current message is M1, for example, this consumer will not get dispatched any earlier messages. Instead, it stays there in post state until everything before M1 gets acknowledged. So this is because if there are failures, we don't want to get messages, all the messages to get replayed again. So we just let everything drain up to that point, and from that point on, the new situation and the new assignment will take effect. The side effect of this is that if there are unacked messages, this will slow down the ramp up of consumers. Say, for example, like if one application does not, one consumer of this existing consumer, it is slowly going through the backlog, and you add more consumers, this consumer will not be able to process the traffic right now. They will have to wait, and that's kind of like unfortunate thing. So, but it's the only way that we can guarantee the ordering. And that also means that if your consumers forget to acknowledge a message, and that message stays unacknowledged, then adding new consumers will not do effect. So if you see the case, just take a look for consumers that are either stuck or they're not, or they're slow and behind, and that is the reason why new consumers are not able to jump right in and start processing traffic. They will do that once everything before the point when they joined will be acknowledged. At that point, they can take part of the processing as well. So hopefully that explains some of the considerations and gives some hint on where to investigate when you see these kind of scenarios. And since this So all this complicated logic to maintain the ordering is so it can be like if you have like a very long acknowledgement cycle, say that if you receive a message and takes minutes or like 20 minutes, in some cases we've seen for depending on the application to acknowledge message, that will slow down for 20 minutes, right? So, and if you don't need the ordering, then there is another setting that you can apply here. So it is called like this relaxed ordering mode. Essentially, like you might not need ordering, but still you might decide to have the stickiness. There's several application cases in which that might be true. For example, like you might want to get the same key to the same consumer always, but you don't care whether it is out of order or not. And that might be because you will just have a might be able to discard the out of orders in the application. And you, for example, like if you just want to update a cache, you might just want to apply the last write win, so you are able to discard earlier messages because of a timestamp, for example. Like in that case, you don't care about ordering. You can apply those updates and just have the last write win based on that timestamp. So if you don't need the ordering, you can basically avoid all this logic of posing consumers by saying that allow auto for delivery equal true. That you do on the KeyShared policy. Once you do that, basically, since we don't have to guarantee the ordering, we can basically a consumer joins, we can immediately do this reassignment of keys and move much faster and not be blocked by the by any slow consumers. So that was kind of all from this presentation. I'm very happy to take any questions on KeyShared, on how it works, or like a more deep dive, or like any other questions. And while you're thinking questions, I would just say that we are indeed hiring, and so if you want to work on these kind of problems and this kind of technology, just talk with us. Reach out to me on Slack or by email or on Twitter, or check out the job posting that we have. There's a lot of interesting problems to solve and a lot of cool technology to build. So I think there is one question, Tai Meng.
Go ahead, you can talk.
Okay. I just want to make sure I understand something. When we're talking about message keys, are we talking about, so I can see that when we use a typed message builder, we can set a key and a value onto a message. Is that the key that we're talking about?
Yes.
Okay.
So this is the same key that is used for partitioning. But yeah, so that key is a message set key. Okay. There is also like an ordering key, so you can also have two levels of keys if you want. So there is key and there is ordering key. You can have two levels, but if you don't specify, if you just want, if you're fine with one, the set key is the one.
Got it. I have an unrelated question, but maybe I'll ask in the end once you're done with the presentation.
Okay, sure.
Okay.
Matteo, do you have more, or do you want to just take the question now?
I'm taking a question. Yes, I'm.
Okay.
Okay. So can I ask my unrelated question now?
Sure.
Okay. So some time ago, I attended a previous presentation and asked about a Pulsar ticket that I filed for the Pulsar Python client, which had some problems with Avro schema support.
Yes.
And so back then you said that StreamNative or maybe some contributors might try to get the fix in 2.8.1, but I don't think I saw any of that in this presentation. I'm I'm wondering if maybe it's now been pushed back to a later release.
I see. So 281 is being cut right now. So if it was merged, then it should be in 281.
It's not. It's not even assigned.
Okay. So okay, I think you reached out on the open source Slack, but I didn't get the time to get back to you. Let me reach out to you, and we can like look at this ticket after this talk, right? Because so we do have in 281 several fixes on the schema declaration. I'm not sure that they will solve that problem, but there have been several fixes on how do you declare the schema and on the Python side, right? Because it is pretty much handcrafted there, since there is no like Java project to extract it from. Can you? Okay, I reached out to you, and we can check that ticket.
Sure,
Okay.
We can talk on Slack. Sure, we can do that offline. Yeah, thank you. All right, so that's it for my questions. I'll mute myself.
Okay. Any other questions, either on KeyShared subscriptions or otherwise? Okay, if not, no questions, I will close it here. But again, just feel free to reach out with more questions later on.
Oh, actually, I was wondering, are these sessions being recorded? I see that recording is on. So like, will it be available for viewing offline future time?
Yes, it will be available on YouTube in our channel, and you'll be able to see it there.
Oh, what is the name of the channel on YouTube?
StreamNative. Good question.
Yeah,
I'll do a quick search now. Yeah, that would be really useful.
If you look on the main page for StreamNative, you will find it out there.
Okay, I'll look for it. If I can't find it, I'll ask you in the Slack channel.
Sounds good. Thank you. Anything else? Okay. Thanks, Mateo. Thanks everyone who joined.
Thank you.
Yep.
Thank you. See you. Bye-bye.
Bye-bye.